Hi, and welcome to this quick tool review. This time around, we're going to take a look at a very unusual tool that's not really machining related, but definitely has some amazing machining included in it in order for it to work the way it needs to. So what you're looking at is my first welding project, which was a fiber optic termination cart for work, and it's specifically fusion splicing. And what you're looking at here is the fusion splicer we bought here at work. This fusion splicer is a Fujikura FSM 60S, cost about $15,000. You can see the design there. I'm not going to show you details about this because this is not what I'm reviewing. This is an optical cleaver that we bought for it. The optical cleaver makes sure to cut the fiber perpendicular to its axis within a fraction of a degree. They use these extremely sharp carbide discs, which are replaceable here, and this one's fallen out of its protective case. That's not good. Each section of the disc is good for a few hundred cleaves. I need to put that away. It's very pretty, polished. So this is about $500. There's Kevlar scissors here. Battery pack for the unit. That was another few $100s. You've got Miller cladding stripping strippers, and some optical prep pads that you use for cleaning the fiber and the various operations. So the reason I'm showing you all this is the hot strippers, well over $1,000, 500, 15,000 quite a few years ago, 50 bucks a piece kind of thing. So all this, you're looking well over $16,000. And the reason I'm showing you this is because Vevor sent me a fusion splicer review, and they sell their fusion splicer for under 900 bucks. So let's see how well it works. If you're wondering why I showed you the Fujikura fusion splicer first, it's because I wanted to be able to give you a comparison between high-end, top of the line, and what Vevor has to present. So supposedly, this kit includes everything you need. So we're getting a first look at exactly the same time. I have not opened this yet. All right, so it's a beautifully laid out kit, very similar design with some foam inside and very similar to the way the Fujikura is laid out. So the fusion splicer even has the same handle, and the layout is very similar. There's a bunch of different layouts of these fusion splicers. This clearly was patterned after the Fujikura just by looking at it. So let me, I guess, take this out of here. So here's splice sleeves. So where the glass fibers meet, you're basically doing fiberglass welding. You fire an arc between two glass fibers, push them together, then pull apart slightly, and it mates up the center and the cladding correctly. And it's fragile, so these fusion splice sleeves have a piece of stainless steel in one section and then a second tube on the inside with adhesive, and you heat shrink it down. That's done in the back of this guy right here. I don't know if you can see that here. That's done in the back right here. That's the splice sleeve melter. And it has adhesive that melts over both fibers to hold them in place, and they're supported by the piece of metal in here, in each one of these. They provided strippers that are a copy of the Miller. They're not Miller, but at least they don't say they're Miller, but they're copies. A dust to blow stuff off. Power cord. That unit supports battery operation, and they include the battery. This was like a few $100 option on the Fujikura. 7.8 amp hour battery pack. That's really nice. Got some cotton swabs. Alcohol dispenser. Very nice. Holy cow. Okay. Yeah, I've got my own alcohol dispenser that I use, but it comes with an alcohol dispenser. Car charger. AC wall wart. Cleaver. Remember I said this was over 500 bucks. Comes with a fiber cleaver. I don't know how good this one's going to be, but we'll give it a shot. It's got a stripper. It's yeah, 0 to 125 micron. So I'll explain a little bit about fiber and why you're stripping it in a short while. I don't know what this is, a support plate of some kind. Some wipes. A brush, tweezers, and a razor knife. Okay, interesting. So pretty complete kit. Comes with everything you could need. In the top of the case, they have a optical stripper of a style I've never seen before. The splice sleeve support that fits on the back of the splicer itself to hold the sleeve as it cools off. And an extra pair of electrodes, because the electrodes have a finite lifetime. They're good for a few thousand splices, supposedly. Looking at the splicer itself inside, there's the splice sleeve oven, if you want to call it. And here, this is the main lid, and you always want to keep it closed to keep dust out. These are the two anvils where the fiber sits. Let's see if we can zoom in and get a closer look at that. So there's the two electrodes that you can replace at some point when they go bad. You get thousands of splices kind of thing, at least on the Fujikura. There's two anvils, precision anvils there that are the positioning anvils that hold the fiber. You feed the fiber in here, go up against the stop, press the cladding against the stop, and the glass itself should be on either, like the glass coming from this side should be on this side of those two electrodes, and the same for this side. And then this thing will move the fiber in right in between the electrodes and then fire. Also inside here is a camera and a light source so that you can actually see the core, or the unit itself can see the core of the fiber and the cladding to align it accurately, and that's what you see on the images that this thing produces. All right, well, let's give it a whirl. And what I'm going to do is I'm going to take you through some basic fiber information so we're on the same page, so you understand what's going on. So I wanted to talk about really quickly about how the fiber is made. So on the outside of the fiber is a jacket, and it's 900 microns. And this 900 microns is to keep water out and to support it. And that's also 0.9 millimeters. And then under that is a buffer, which is 250 microns. And 250 microns translates to 0.25 millimeters. And that has a similar feature. I think that's the interface between the actual glass part of it and the jacket. So the cladding of the fiber is 125 micron, or 0.125 millimeters. And the core, depending on whether it's multi-mode, reduced mode, or single mode, is 62.5, 50, or 9 microns, which translates to 0.062, 0.052, or 0.009 millimeters. Now, the reason I wanted to show you this is because multi-mode, the core is 62.5 or 50 micron, and easier to align than single mode, which is 9 micron. Single mode fiber goes the longest distance, but it's the hardest to get light into, but it is best quality. The fusion splicers come in two varieties, well, three varieties really. So for each variety, they either have a cladding alignment where they get this outer glass part. The green and the red are glass, the rest are some sort of plastic or resin or something like that. So the glass portion of it, some fusion splicers align on the cladding, and the core may not be dead center, so the alignment isn't perfect, and so you get a lot more loss. But a much more expensive kind of fusion splicer is the core alignment, which is the one Vevor sent me, is a core alignment, and it aligns either on the 62.5, 50, or 9 micron for single mode core of the fiber. And it has a camera built in that will you'll actually be able to see both cores line up. And at least that's the way it is on the Fujikura. I haven't used this one yet, but we're about to, so we will see. One thing to note is that alignment is done in multiple axes, and it's truly an amazing feat of engineering that they're able to pull this off, which is why they were so expensive originally. I'm not sure how they got the price down to 800 bucks. I said 900 bucks early. This one's actually 758 bucks for the entire kit. Just a truly astonishing value. So if it works, so we're going to find that out right now. What I'm going to do is I'm going to take a single mode fiber. We're going to start with the hardest case. We're going to take a single mode fiber, And we're going to splice. First, we're going to measure the loss through the fiber, and then we are going to cut it, fusion splice it, and see what the loss is after we're done. A good fusion splicer should be able to have only about 0.1 dB loss. In a fusion splice, 0.1, 0.2, 0.3 I've seen, but usually 0.1, 0.2 dB loss. So we will see how that works out. So like the Fujikura, this unit needs to calibrate based on local temperature, humidity, and everything else. And so you have to do the arc calibration before the first splice, and they're warning you that right off the bat. Oh, that's funny. It's straight in arc correction mode. In the Fujikura, you'd actually have to select the sub menu to get there. This just took you right there. And basically what you do is you strip 2 single mode fibers and you clean them and you get them all prepped and you put them in the splicer and it'll do an arc calibration. It'll destroy the ends, but in the meantime, it figures out where the arc should be. So we've got to prepare some fibers first, which I will show. All right, so I got the fiber loaded in here, stripped back 2 pieces. We're going to do the arc calibration. This is sacrificial fiber, so hit this. Ooh, and you can see under magnification what it looks like there. That is not clean. So I have got to clean these fibers first. Okay, it's running arc calibration. That was the calibration complete. We should be able to splice the fiber. Here's what's left of the fibers. I don't know if you can see that after the test. You have to be very careful with this glass because it can stab you like a splinter and doctors can't see it to remove it. So it's total pain. So be very careful with these. The way the splicer is currently set up, the moment you load both fibers, so you lift this lid, you load one fiber in. Then when you load the second fiber and lock it down and make sure they're lined up visually correctly, the moment you close this lid, it automatically tries to do a splice. I prefer having it set, lack of both fibers, because it just tried to do a splice. What I like to do is I like to have the unit set up so that you have to step through. Initially, you want to see the fibers aligned. You want to see them checked for angle and all that sort of thing. Make sure that there's no dirt on the fibers themselves. And then I want to splice when I'm ready. I don't like to do automatically. It makes for really convenient splicing. So there's not a problem as far as that's regard. Like if you're trying to do 100 splices, you know, you probably don't want to wait for each one, although I think I might because I like to see everything and make sure it's good. You're currently set for auto on this guy. You can set it manually to a particular fiber type. Let's see how you'll select. So you can pick like single mode and all of these other different kinds of fiber types. There are 4 pages on here. And you can make custom ones as well for specific types of fiber and specific classes. So let's see if I can set this auto heating on, auto starting. See, I'd probably like auto starting not to be on. Auto save splice image, that's interesting. For splice, screen rotation, operation beep. Auto starting, I'm going to put it off. So I don't want it to start automatically. I want to be able to step through using the buttons up here. So I'm going to leave that set that way. Tension test. See, at the end of the splice, the two pieces of fiber are brought in real close proximity. An arc is fired between them and creates a plasma which melts the glass. They're pushed together so the glass on both sides can meet very precisely, and then pulled back just slightly at the end to stretch it out and make it all even. And then once it cools, once you open the lid, once you do this, the unit will do a tension test and it'll actually pull on that junction to make sure that the glass was melted properly. And then it evaluates optically whether the splice was good or not. In this menu here, I was looking under splice set because the Fujikura, when you're looking at the 2 optical fibers coming together, they show you the surface angle in 0.1 degree increments, and this one obviously measures it because they've got a 0.8 degree threshold for individual fibers, and the surface angle 1.5 degrees to make sure that when you push the two pieces to glass together, that one's not coming like, or well, imagine that it was cut at an angle. So when you put it together, one piece is effectively meeting like this. They don't want that to happen because you won't get a good splice and your core won't actually be touching. They want a, you know, a hermetically sealed meeting point of the glass core of the fiber. So that's very important. And so you can choose alignment mode to be core or cladding. I don't know why anyone would want cladding. It's faster and it's easier, but then the core is not necessarily well aligned. For multi-mode, you can get away with that. Single mode, definitely not. Then you've got replacing electrodes, arc correction, light correction, splice records, all that sort of thing under maintenance. This is a full-fledged, fully loaded unit, and I'm currently running it on battery. It's not plugged in. So that's really handy if you're out in the field and you need to put this someplace strange. And remember when I said the arc calibration, it needed to know everything about the environment. You notice here it's saying 55.8% humidity, there's the pressure, and there's the temperature. It needs to know that in order to get that plasma arc correct, because it's a very, very precise operation, so it has to be right on the money. So all I did was take that store-bought fiber and cut it in half, and now we're going to strip the two sides so we can splice them. And so the first step is you need to remove this outer protective layer. This keeps water out of the fiber, also provides containment for the strength member, which is Kevlar. And so this has 3 different sizes on the stripper, and the largest size will strip this portion here. Now, I just carefully break through. I don't even bother closing it all the way. And another thing is that the Kevlar inside here can become a total mess. So one of the tricks I use to keep the Kevlar contained is not remove this all the way. And that lets you take the Kevlar and take these little tiny fibers that could easily become a huge mess. And I'll show you after I'm done what kind of mess they can become. And you just pull them to one side, and then the kit didn't come with this, but you can use regular scissors. These are specifically designed by Miller for cutting Kevlar, and they even struggle a little bit. They're serrated, and you have to keep the Kevlar under tension or you won't be able to cut it, because this is actually made up of a ton of small strands here. And just to show you, this rapidly, if you let this end just go, trying to get through this mess is absolutely insane, because they're really, really strong fibers, as you can imagine, with Kevlar. So but they're so fine that most scissors, they'll fit in between the scissor and they won't actually cut. So that's a trick to keep the fiber separate. So then, once you've done that, now you've got the jacket on here, the 900 micron jacket, and the buffer, which is underneath that, which is a plastic coating, and you need to remove that to get down to the glass. And you need to remove about like that much fiber. That's like, I don't know, 30 millimeters, a little over an inch, inch and a quarter kind of thing. So you take small bites. With this, it can be a trick with these kind of strippers. There we go. We got the first part, but actually you can see, or actually maybe you can't see, I don't know if there's any good way to show this, but there's some plastic. That's that inner buffer still left on the fiber. You sometimes have to make another pass. So let's see if we can get this here. So you pull and just stretch that off there. It's actually doing a pretty good job of cleaning it this time. If you're not careful, and I go at an angle because it makes it engage better. At least I found it makes it engage better. But if you're not careful, if you nick the glass, it'll break where you nicked it. I don't know if you can see this. So you can just see like a little, maybe you can't, if you, against my hand here maybe, see that little white part on there? That's actually the buffer still remaining. So while I'm holding this, should have had this prepped to begin with. Take the Optic wipe, and I have a container like similar to the one that came with the kit of 100% isopropyl. This already has a bit of alcohol on it, but you've got extra alcohol doesn't hurt. You need to keep this clean, and you need to keep water off it. Now hear that sound? That's me pulling on the fiber with the clean pad. And you want to do that because you want it to be very clean. And you need to clean it before you cleave it, because if you clean it after, you could get dirt on that pristine cut surface. So here we are with this. So I'm holding this. So you finish all of these operations at one time. You don't go on to the next, like you don't set this down and then move on to the next one and try and do that. You finish all of this at one time. So the next step is to put this in the cleaver. I'm trying to do this upside down so the camera has room to fit here, and so you can also see at the same time. There is a groove just for this fiber, and I want this at 13 millimeters right there, and put this on hold. And what this does is there's rubber pads here and here and on top. When I close this guy, the rubber pads hold the fiber in place, and you want it to be as perpendicular as possible, because you can see that if this isn't straight, it'll be at an angle, and an angle will make a non-perpendicular fusion splice. And if you're off more than like 1.8 degrees, it's not going to work. So then this closes and a magnet holds it down. And all you do on this splicer is push this forward, and supposedly it nicks the fiber. I don't think this one's quite adjusted right from the factory, although actually it did cut. Okay, what I didn't realize with this particular cutter was that you need a lot more fiber sticking out, because with the Fujikura, it's an automatic thing. So you preload it and then you hit a button and it clicks and it just moves this wheel right across the fiber. You can get away with a lot less fiber sticking out. With this one, the fiber needs to stick out into this collection tray, and be very careful with the fibers because they are really sharp. So once I've got this fiber cleaved to the right length, as you can see here, I need to take and immediately put this in the fusion splicer. You do not set this down. Because it is this surface at the very end here, which you obviously can't see, is a cleaved and clean surface that's just been prepared for mating, and you cannot afford to get anything in its way. So here's the fusion splicer. So I'm going to take this guy and I'm going to preload this, and it's still a little long, so I'm looking here. I know that this thing needs some range to work with. So normally, if I cleave this correct length, then this orange buffer, you could just push it up against the end here. But in reality, that would have the glass going past the electrodes here, which would not be good. So instead, I pull it back so it's just on this side of the electrodes, and then close the clamp that holds it down. But you want it to be straight. And there are anvils here. The top will close anvils on top of it and hold the fiber in place. There we go, that looks right. Now I just need to prepare one more, and then we can get to splicing. As I'm getting ready to prepare the second fiber here, so I'm going to slide this out of the way. As I'm getting ready to prepare the second fiber here, I realized I almost made a rookie mistake. Did you catch it? I'll show you coming up real quick. So again, same sort of thing. In fact, I'm going to leave this one even a little longer. Pull this out, pull back my Kevlar, try and make sure I get all of the strands. Pull tight. Pull this guy out. Oh. And here's what I neglected to do last time. You need to do it once. I recommend you do it the first time. If you try and put on the sleeve after you've cleaved it, you will ruin your cleave point. You'll get debris all over the end of that fiber. It needs to go on before you strip it and before you cleave it. And I neglected to do that last time. Easy mistake to make, but definitely will cost you. So here again, we're going to strip the fiber, taking small bites. I tend to hold these at an angle. It just seems to work better for whatever reason than just perpendicular. I don't know why that is, and maybe it's not quite right. I was never trained formally. Again, on this one, I can see there's a little of the cladding still on here. I'm sorry, not the cladding, but the buffer still on here. And sometimes you can just take the buffer off with your hand. If necessary, you just take another pass with these guys. Okay, there we go. Now, clean it. It's amazing how much noise can come from something that's only 125 microns in diameter, right? That's a 1/10 of a millimeter right there. Okay, so we're ready to cleave this guy. So this outer jacket here, it tends to, when it's cold, it tends to curve. And that's a problem because, again, like I mentioned the last time, you really want this thing to sit flat. That's why it's got this whole groove in here. Because if it doesn't sit flat, then you'll be at an angle and you won't get a good splice, and it may fail. The splice may actually fail. So close this, cut that, open it, and again, I actually did a really good job. I made this one shorter because I'm trying to get that length right. Bring this guy back. Could have turned this on. I had it off while I was doing this. That's almost a perfect length. I almost got it right on the money that time. Okay, so in the past, when I closed this lid, this thing tried to immediately do the splice. Now it's waiting for my input, which is good. So splice program, we've already got it selected, so let's go back. So let's see. Now I've never done this manually. Now that I switched it over to manually, oh, you just go here. So there you can see both ends of the fiber. So one window is from looking at from the X direction, and the other one's looking at it from the Y direction. And it didn't give me an opportunity to look at it before I decided to splice, but it says 0.00 dB. Outside here, this black area, that's the cladding. The center little white section is the core, 9 microns across. And this says that it was a perfect splice, essentially no loss at all from what it could tell. So now I'm going to show you when I open this guy. Let's see if I can get this so you can see it. So when I open this guy, immediately these two ends pull out and start tugging on the fiber for a tension test. And I pop these open. And you can see the fusion spliced fiber right here. And I immediately take the splice sleeve and I put it over both. Try and get it centered somewhat. I close all of this. You want to keep this closed as much as you possibly can because you want to keep dust out of there. You open up the heater, and the heater is set to automatic, so when this guy goes in, it's just going to start automatically. Takes about 13 seconds for it to heat, and then it'll cool down after. It's heating a heat shrink tubing, and inside the heat shrink tubing is glue, and that glue is also melting, and it will hold the fibers in place in the shrunken sleeve. And it's already done. So you pop this guy out and you let it cool. And a perfect splice. So before I did this, I measured the fiber optic cable with the power meter and the light source and the power meter. And then I nulled it out like a tare on a scale, set it to 0. Let's measure this and see what this one measures. It's basically saying that this fusion splice is 0.01 to 0.02 dB loss. And here's the splice right here. You can see the whole fiber on screen. I just cut it in half. I left the connectors in place. Thing is, as you move this around, it can change dramatically. All these things are very, very persnickety. And so, but you can see that while it was nulled out there, that we had a really good fusion splice. And so the $750 fusion splicer performed as well as the Fujikura that, 15 years ago we paid $15,000 for. I'm going to give it a big thumbs up. For the money, that's a really good deal. Now, I don't know how many splices. It's supposed to be good for thousands and thousands of splices. Eventually, you have to replace the electrodes. They gave you a spare set. So the kit as a whole includes a lot of parts. Obviously, it doesn't include these power meters. Bottom line is, this Vevor fusion splicer is a really good deal.